Welcome back to the QEF channel for a new episode on our cycling studies. In our recent investigation, we examined the impact of switching to a 165 mm crank arm from the previously used longer lengths. The results showed improvements in both biomechanical and aerodynamic aspects. In this video, we will focus on the aerodynamic findings, while the biomechanical aspects will be covered in a separate video. First, we'll discuss how the shorter crank arm affects bike setup. Then, we will explain the results from two CFD simulations comparing the different crank arm lengths. Finally, we'll explore the concept of frontal area and the challenges in interpreting it. When a cyclist switches to a crank arm that's 10 mm shorter, one of the first questions they face is how to adjust saddle height. Should it be lowered by 10 mm, left unchanged, or raised by 10 mm? From both a biomechanical and aerodynamic standpoint, the best option is to raise the saddle by 10 mm. In this way, when the pedal reaches its lowest point, it is 10 mm higher off the ground than before. Since the saddle is also raised by 10 mm, the leg remains in the same extended position. However, when the pedal reaches its highest point, it is 10 mm lower than before, while the saddle remains elevated. This means the leg is more extended, 20 mm in total. If the handlebars stay unchanged, the rider will naturally be able to rotate his torso more. This helps restore the original angle between the torso and thigh at the peak of the pedal stroke, leading to a more aerodynamic position. For this study, we analyzed 7 high-level competitive cyclists who adopted the new position during winter training. Their routine included road training as well as bi-weekly sessions focused on stretching and core stability. After 6 weeks, they were reassessed in the lab. While the biomechanical data was averaged across all subjects, the aerodynamic simulations focused on a single representative cyclist. He transitioned from a 175 mm crank to a 165, and his physical characteristics are detailed in the table. To create a digital representation of the cyclist, a 3D scan was taken while he was standing in a neutral position. This model was then refined in Blender 3D, where unnecessary details were removed to prevent errors in the simulations. A mechanical skeleton rig was then added, creating virtual bones to control body movements. While it takes more time up front, it allows more realistic cycling postures and enables adjustments for future simulations. This approach is especially useful for accurately representing lower limb angles during dynamic movement and under load. In contrast, a 3D scan of a cyclist in a static position on the bike wouldn't capture the true joint angles, as it wouldn't reflect real motion or force conditions while riding. In cycling aerodynamics, the projected frontal area serves as the key reference. In this study, it was measured using an orthographic rendering of the 3D model representing the body's effective shadow from an infinite distance. In the standard riding position with 175 mm crank arms, the frontal area was 0.444 square meters. Switching to 165 mm crank arms, it reduced to 0.437 square meters, a 1.6% decrease. This 70 square millimeters reduction was mainly due to the head overlapping the torso and the silhouette, and more importantly, the greater horizontal inclination of the trunk. Changes in leg positioning between the two postures had a negligible impact on the frontal area. While frontal area measures the surface directly exposed to airflow, a broader metric accounts for all body surfaces facing the flow direction, even partially occluded areas. This includes sections like the abdomen behind the arms, the knees behind the hands, the upper chest behind the chin, and the back of the neck and shoulders behind the helmet's shadow. This measure, which we will call normal area, was also calculated. With 175 mm crank arms, the normal area measured 0.473 square meters. Switching to 165 mm crank arms reduced it slightly to 0.470 square meters, a 0.6% decrease. An animation of top views for both riding positions highlights how the back area exposed to airflow, shown in red, increases with 165 mm crank arms due to a greater torso rotation. However, this increase in exposed shoulder and back area is offset by a greater reduction in the thorax and abdomen area, thanks to a more tucked posture. The simulation were conducted using the 3D model of the selected cyclist without the bike, riding at 14 meters per second, which corresponds to 50.4 kilometers per hour with no lateral wind. Looking at the two images, 175 mm crank arm position on the left and 165 mm on the right, we can analyze air velocity near the body. As explained in a previous video on BOA systems in cycling shoes, airflow remains attached to the body as long as it stays fast. The longer it remains attached before separating and forming vortices, the narrower the wake, the lower the suction, and ultimately the lower the drag. Regardless of crank length, the raised legs gluteus on the right side is more aerodynamic, as indicated in red, than the left. With a longer crank, the leg lifts higher, further enhancing the aerodynamic advantage of the gluteus on that side. This is visibly demonstrated in the comparison. The gluteus appears redder in the image on the left. Next, we observe the central part of the back, where airflow shifts left in one image and right in the other. This variation isn't due to body position, but rather natural oscillatory movement in the airflow. Depending on the precise moment captured, the results may be slightly different. Notably, this zone is redder with the 165 mm crank, meaning that at the shoulder and scapula level, air stays attached to the body longer. In the next set of images, shear stress coloring illustrates frictional forces as air slides over the body's surface. Dark blue zones, where shear stress is 0, indicate regions where air has separated and no longer generates friction. These observations align with our previous findings, reinforcing the aerodynamic advantages of the 165 mm crank setup. These images provide a side view, showing air velocity across a planar section. The difference in these blue areas are simply a natural fluctuation in airflow direction over time, which we already highlighted in the previous top views. The upper back is redder in the 165 mm crank position, indicating better airflow attachment. These new images, enriched with LIC lines, provide a clearer understanding of flow motion. One final observation concerns helmet aerodynamics. In the 165 mm crank position, where the head is tilted downward, the helmet's performance worsens. This is evident from the larger upward wake forming behind the helmet in the right image. A more aggressive position would likely amplify this effect, revealing a flaw in the helmet's design. Improved helmet aerodynamics could further reduce drag for cyclists using the 165 mm crank setup. The total drag force, which opposes forward motion, was 3.38% lower in the 165 mm crank position compared to the 175 mm. Drag consists of two components: pressure drag, which acts perpendicular to the surface, and viscous drag caused by friction, acting tangentially to the surface. As shown in the table, pressure forces dominate over viscous forces, which is typical for bluff bodies like a cyclist. Both the frontal area and drag coefficient, which together determine the drag area, were analyzed for both definitions of exposed area, the frontal area and the normal area. Using the frontal area, the shorter crank position reduced frontal area by 1.6% and CD decreased by 1.64%. This means the aerodynamic improvement was equally due to a reduced surface area and a better shape factor. Instead, using the normal area, the exposed area decreased by just 0.64%, while the CD improved by 2.75%. In this case, the primary improvement came from a more aerodynamic body position rather than reducing surface area. While certain elements, like the helmet and lifted leg gluteus, had less drag in the 175 mm crank position, the overall aerodynamic performance was better with the 165 mm cranks. The key improvements came from a more inclined lower back, a streamlined torso, and a reduced exposed area. This study also highlights how the definition of exposed area significantly affects the interpretation of results and should be evaluated critically. Additionally, the findings suggest potential improvements in helmet design to better accommodate aggressive riding positions. Stay tuned for upcoming videos where we'll tackle some of the open questions raised in this study.